Our next speaker is David. I met David at a ground engineering conference last October, and I'd just come from Cambridge at the Cambridge Institute for Sustainability Leadership, and they'd been hammering me with the tree hugger, we're destroying the environment stuff. And then I went to the ground engineering conference that had this very big theme about sustainability. And the longer the conference went on, the more depressed I found myself, thinking, I'm in the wrong industry. All we do is dig up masses of earth and then put in masses of concrete and steel, and the embodied carbon on every single basement is insane. And then I heard David speak, and he made me feel quite a lot better, and I thought, actually, there is options, there is promise. So it's great to have David come and speak to us. David is the head of ArcelorMittal sheet piling, and they are one of the globe's biggest steel companies. And David he's a fellow of the Institute of Civil Engineers. He recently was the chair of the steel piling group. He's on the British Standards Committee, and so he's very competent and experienced in the field of piling and sheet piling. He's also got 20 years of geotechnics and ground engineering experience. Outside of work, apparently, David likes photography and travel and marathon running. So if you want to make small talk, do that. Will you welcome David?
Thank you, Ben. Thank you for the PCA for the opportunity to speak. I haven't travelled too far today, actually. I think less than 10 miles, so not much chance to do that now. But thank you for having me here, for that introduction. So I'm going to talk a little bit about sheet piles. I'll just give a very brief overview of some of the applications of them. I'll touch on the waterproofing aspects of it, but that's your speciality, not mine. So please go easy on the questions on that area before I move on to the sustainable aspects of the steel. Steel piles are, in simplest terms, are a hot corrugated sheet, and they're particularly defined by the interlock, which allows us to join them together, allows structural connection, and allows us, or helps us to keep water out. That's in their simplest terms. Some of the things they use for at the bigger end, I'm only showing this because this is the start at the big end and work our way down, but this is the marine sector. We're not so interested in keeping water out there. In fact, often the opposite. We're trying to allow water through and relieve some of the pressures there. But just for a sense of scale, that cross section that you can see there is about a 20-metre retained height. More familiar on land, you might see railway cuttings, motorway cuttings, bridge abutments. Of course, a basement there, there's a nice car park, and one other area where we are trying to keep water out is a flood defence. That's a big sector for us as well. We look at temporary applications a lot with sheet piles because they are reusable. They can be extracted, reused. So some examples, cofferdams on land or in water. And the other reason that we talk about them for basement construction is the installation. It can be low impact, it can be low noise, it can be low vibration. You can see on the example on the left here, it's right next to a bus route. There's actually a tube line beneath there, and there's people living and working nearby. Those piles are being installed in what we call a silent vibration-free process. It's a hydraulic press that's putting it in. So it's not always the image people have of piling is often a big hammer hitting the piles. That is one way of doing it, but we can do it other ways that are more sensitive. And of course, if we're doing a basement, then waterproofing is a key topic. The steel itself is not going to let any water through. Our weak point is that interlock, and there's various ways we can deal with that. And ArcelorMittal, as Ben says, we're a big steel producer. We're the largest producer of sheet piles And as that, along with that comes a responsibility. So we publish a lot of guidance. You might be familiar with the piling handbook. We have a separate guidance on keeping water out of excavations with sheet piles. A big part of that comes from how we seal the interlocks. There's some brand names up there, but effectively there's 3 different approaches that we have. One is a displacement filler. So we fill that interlock with something. The simplest type is a type of bitumen that fills that interlock and doesn't allow anything else through. Then there's water swelling hydrophilic sealants that can be applied. The important thing for us there, it then gets very involved in the installation. The sequence of installation is what's important when it comes to that. And the highest level of sealant is a compressant sealant. So you can see in the bottom left, there's 3 lips of sealants that are applied on there. It looks like someone's gone and squeezed toothpaste into the interlock in 3 very strategic locations, which means that however those interlocks are aligned with each other, there will be at least 2 of those in compression and creating a very high degree of seal. It's not just the vertical sealing. We can help with details for connection into the slab as well. But to talk about the sustainability, which is really what fires me up. I mean, I'm a geotechnical engineer, as Ben says, but what I found fascinating, the big area of progress recently for us is in the sustainability. And if we set that against what should be familiar for a lot of us, the hierarchy of waste. So the first thing we should be doing is we should be avoiding doing anything if we can. But we're all here because we build things, aren't we? Or we're involved in building things. So we should be reducing what we're doing. Then reusing what we can, and then if we can't reuse, recycle. So the sheet piles reducing, there's a number of different things we can do. We develop a higher steel grade, stronger steel, if you like, to maximise the strength of what's in there. That's a nice, easy first step. Optimising the shapes, and I'll show you a slide in a minute, it shows some of the way we tweak the geometry of the sheet piles. They look very similar. Every sheet pile to an untrained eye will look very much the same, but I'll show some advantages that are available there. The bit that really gets me excited, the geotechnical design. We can be smart with what we know about the ground or the water in the ground. And back to the installation methods, we can get clever at that, and that all helps us use less steel in the first place. The sales part of my organisation hate me for doing that because I spend a lot of my time trying to sell less rather than more. So the shape of the sheet piles, this shows a progression through time. We've been making sheet piles for over 100 years. Left to right, you can see that they're, in simple terms, they're getting a little bit wider, a little bit deeper. And what that allows us to do is get more for less. So one example, the AZ50 was 10 years ago, was our biggest, our heaviest, our strongest sheet pile, shown in the yellow there. Just by making each pair of piles a little bit wider, it's gone from 1160 to 1400 millimetres for a pair of piles, marginally deeper. So there's 20 mil difference in the depth. If you know a piling installation spec, you know that's not even noticeable on site for how accurately they have to put them in. But we're getting over 6% saving in the weight. If you get 6% saving on everything you do, you're going to it starts adding up. So that's just showing it as a cost saving, never mind a material weight. Reuse is simple. I had a discussion earlier today about the reuse. We can pull the same equipment that you put piles in with, you can take the piles out with. It's great in a temporary works application. I've showed these before. It's temporary works. Typically, sheet piles will be used 10 or more times in temporary works. Things can be programmed that you can take them out at the end of life in permanent works as well. It does depend a little bit on what you do, what you build over the top of it. But in theory, they can come out, and they are an asset in the ground. One story that I used to hear when I first started in sheet piling was there were a couple of sites that had piles in the ground for 10 years, long enough for the price of steel to have gone up so much that when they came out they were worth more than when they went in. Not always the case, I'm making no promises on that, but it is a resource, and it can come out and it can leave a clear site. Which leaves us with recycling. It's where we can maybe make the biggest difference day to day on what we're doing. And steel, great. I think after, a little code on that, the most recycled material in the world, after water maybe. I think we've all heard how many times your glass of water has been drunk by somebody else before you. But steel is infinitely recyclable, and with no loss of quality. It's not like the early days of recycled paper where it had that horrible brown hue to it, and every time you thought it was recycled, it was going down in quality. There's no change in quality when we recycle. And why do we bother recycling? Those of you that can remember maybe from your chemistry lessons, the primary way of making steel, we're a horribly dirty industry. For every ton of steel made the primary route, which is taking iron ore and coal, adding an awful lot of energy. For every ton of steel that's made that way, there are over 2 tons of carbon dioxide equivalent released into the atmosphere. Now, that's shocking, but it means there's a big scope for improvement. When we recycle, what you're seeing there on the next slide, you're seeing there on the left is an electric arc furnace. So that takes scrap steel, puts it in a big pot, puts a big electric current through it, and that's what melts it. Now, if we use an electric arc furnace to recycle steel, instead of 2 tons of carbon dioxide equivalent per ton of steel, we're down to around about the 500 kilograms mark, a quarter of where we were. Now, what we can do on top of that is we can feed that electric arc furnace with purely renewable energy, in which case that 500 kilos comes down to 300 to 350, depending on the product. So if you think going from 2 tons down to 350 kilograms is a huge improvement. When we do that at ArcelorMittal, you'll see it branded as X-Carb, or for the sheet piles, you see Eco Sheet Pile Plus. From our side, that's what you're looking for. Being non-product specific, if you're looking for things in general, we've heard about EPDs today. Everyone in the steel industry will produce those sorts of that sort of information. Having an EPD doesn't mean that you've got a green product. It allows people to measure how green it is and plug it into their calculations. But one thing across different steel producers, you might see responsible steel as well, and that covers emissions, pollution, responsible sourcing, other social aspects, labour rights and things. So that is something that would help you see when you're specifying a low carbon steel. But we'll look at some of the ways you can calculate further from that information as well. But before I do, let's just get away from some of the dry stuff and look at an example. I've got an example here in the Netherlands, because some of the practice that I'll talk about later is in the Netherlands as well. But this is a nice one. As well, we're talking about sustainability, and everyone knows in Dutch cities, everyone's riding around on bikes. It's lovely, isn't it? It's the green ideal. They often arrive at that city in a car, and they need to park that car before they get on their bike. So this example is in The Hague. It's a 500-metre long car park beneath the street, and it's quite common practice. We've got a number of examples like this. 390 parking spots down there. Interestingly, you can see on the left we've got a sheet pile wall with an incandescent paint on it, and on the right we've got a slurry wall, and that keys in nicely to the study that I'll show in a minute as well, where we look at some different aspects. So to study the difference between the different construction methods and some of the relative advantages, we had a study which Royal Haskoning did for us 4 or 5 years ago. And this was looking at, it's multifaceted. We were looking at the technical aspects, at design, at settlements, at fire safety, all those things that might need to be considered in a design. Obviously, from a client perspective, they're interested in the cost So we did some cost comparisons on these. And relative to what I'm talking about today, some of the environmental criteria were looked at as well. In terms of the technical side of that, it used typical current practice, or typical practice of the time, at 2018, in the Netherlands, typical design approaches to the current standards. The techniques that were investigated were steel sheet piles, secant piles, a slurry wall, and a cutter soil mix wall. A 2 and a 3 level basement were explored in 2 different soil conditions. Some of the outcomes from that were quite illustrative to us. I think ignore the diaphragm wall. From my geotechnical perspective, it was probably the wrong solution to look at. It's over the top for that size of basement, and that's why cost-wise it's looking like a bit of an outlier on that chart. But the sheet 2 on the left, the sheet pile walls with different installation methods, a vibratory one and a pressing. So the pressing was the silent method that I talked about. So it's a little bit more expensive in that study. The using a vibrator, which is still relatively low noise, was a little bit cheaper. I mean, not groundbreaking differences between that and the piled wall or the soil mixed wall, but we're showing that the costs are there. Of course, I'm going to show that the sheet pile is potentially cheaper, but I think they're of the same order of magnitude, which I think is a great place to start. There's a speed advantage to the sheet piles, but that's incidental to the topic today. But one of the reasons it's faster is because as soon as the steel's in, you can build on it. You're not waiting for the concrete to cure. The interesting thing comes when we start to look at the environmental impact. And this is from a separate study, this done by Witteveen and Bos, and this is the global warming impact of the different solutions. And there you can see there is a clear difference between the sheet piles and the other solutions. Again, maybe the diaphragm wall was a bit of an outlier, but we're still at less than 50% of the carbon footprint of those solutions for the same size basement, and it's done in the same way. So it is possible to do. How do we drive that? How do if you have a project, or if you're involved in a project, what can we do to push that agenda? From my perspective as a material supplier, like I say, right the way through the value chain. I use the word value chain, and we've heard PAS 28 as you mentioned a couple of times this morning. And that's one of the terms that they like to talk about. And PAS 20 to me, it's about creating that framework for managing. Its purpose is to create a framework for managing carbon, but it's about driving that collaboration between all those partners and seeing how that can be done best. I've used Dutch examples, and I've put a Dutch approach up there. I'm going to talk a little bit more about how we incentivise the low carbon in a project. That's the really key bit for me. That's the bit that I really like to take away. But a couple of the things I want to mention before I move on to that. I've put up there the ARP model specification. Anyone who's familiar with working with piles might know the IC specification for piling embedded retaining walls, or spur wall. Recently, Arup have written a 2-page addendum to that. It's not a formal addendum, but it's written in the same style as, and it's easy to add on. They've used that with clients like Canary Wharf Group on some of their recent projects, and that allows you to set a baseline for the carbon, which you can then measure against. You can measure your tenders against, and they've done a study with the last 5 projects that they've done, which rather interestingly showed the first one they did at tender stage, widely varying estimates of what it would be from the tenderers. But as they moved along that journey of educating themselves, understanding the materials, understanding the processes, they got better clarity on that, what that prediction was. They also then insist on constant measurement throughout the process. An agenda item on their weekly progress meetings was how much carbon has been used on site this week, and they would monitor that throughout. They beat their baseline in each case. I think in each case the lowest tenderer was the lowest carbon tenderer as well, but it wasn't incentivized that way. It was just to get the background. I think there's one instance where they were above their baseline, and that's because there were some issues on site which meant some rework. But it's giving them a good understanding, and like I say, the interesting thing is that education that's coming through all those partners, that they're able to estimate things far more accurately as time goes on. In terms of estimating, I'm sure everyone's got a carbon calculator of some sort. They've got some way of measuring. There are ones out there that are piling specific. There's one that's done by the DFI and the EFFC, which, like I say, that's piling specific, but it allows you to do those steps. If you want a slightly broader one that's freely available, I know Tony G, who are members of the steel piling group, they've made theirs freely available to SMEs to calculate the carbon up. So this Dutch approach is a way of incentivising low carbon performance on a project, and this is a really exciting way for me to look at a project. And here I'm talking in terms of the sheet piling. It's probably applicable to anything, and it comes down to their government's way of interpreting the European directive, which says that you must consider the financial, environmental and social criteria to choose the most economically advantageous tender. And they